Welcome back to the never-ending chemical bonding. This is part 7, and in this part what we're going to do is we're going to look at the molecular geometries a little closer. I've got some pictures that you can peruse at your leisure. I'm not going to spend a lot of time on them. And then we're going to predict and draw the electronic and molecular geometries. So I mentioned earlier that if you don't have any lone pairs, then your electronic geometry and your molecular geometry are going to be the same. What actually happens is, because if the lone pair is not being shared with something, that it actually has more repulsive characteristics than the electrons that are in bonds, and so what it tends to do is push the structure that is the part of the structure that is bonded away from it. And this affects the bond angles. And when you do that, then the bond angles change the molecular geometry. So only if you have lone pairs in your formula will you see this change. And so here, I just put this on here. This is from your textbook, your TRO second edition. Or third edition, whatever we're on now, that shows some examples. And I like this because it shows you the effect of that lone pair. You have a tetrahedral electronic geometry, and that lone pair, though, changes the shape and makes the molecular geometry trigonal pyramidal. And same, showing over here. So that's important because it helps us decide if a molecule may be polar or not just if the bond is polar, but is the molecule polar. And so I've got them all on here so you can look through them and see, so you can visualize a little bit better in 3 dimensions. So when we're predicting the molecular geometries, I kind of did it quickly before, but you look at the Lewis structure, you look at how many electron groups, then you do the electronic geometry, then you do what we call the AB formula, okay, or the ABU formula, to see if you have any unshared electrons or lone pairs, and then you use the table to determine the shape and the bond angles. So I've got this one kind of laid out for you so you can kind of see visually. PCl3, this is the Lewis structure for it. So you first draw the Lewis structure and you identify that you do have a lone pair here. So if you're following along with the AB thing, the AB formula for this would be AB3 because it's A, and then 1, 2, 3 things it's attached to, and then U because there's one lone pair or one unshared pair. So that tells me that the electronic and the molecular shapes are not going to be equal. And that's because when you have the lone pair sticking up there, that it pushes and repels the rest of the electrons that are bonded and changes the actual bond angles. Because remember, these electrons want to be as far away from each other as they can be. And so those two that are lone pairs aren't being shared with anything, so they have more force, if you will, to change that shape. So here's one for you to do, the practice, the molecular geometry of the ClNO. I'm going to do this one with you because this one's fun. This is ICl4. ICl4. Okay. So I'm going to do the skeleton. ICl4. That's a weirdo, isn't it? All right. And then to see what the actual Lewis is, I'm going to do the NASB. So I've got, and you know how to do these now, so I'm not going to go through all the steps. So 8 times 5 is 40, and then 7 times 5, because all of them are in group 7, is 35, right? Now this is an ion, so that's 35 plus 1 is 36. So shared is 4, and so it predicts 2 bonds. Okay, I see that is not right, so I know automatically that tells me that this is a violator. Can you hear the sound? Whoop, 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 whoop. That's what I hear in my head when I see that. Okay. Okay, so I'm going to go back to, I know I'm crazy. So I'm going to go back to the 36. And then I'm going to put all the electrons on these outer. And I do this because I need to know if there's any lone pairs or not. Okay, so I did 6 on 4 of those. I had 8 originally in bonds. And then I had 24 to fill out the octet. That left me 4. Okay, so I have to put the 4 that's left over on the central atom because that's where it goes. I'm a symmetrical kind of gal, so I'm going to go ahead and I'm just going to do them like this, like across from each other. And you really need to put them like not over or on top of a bond, so like do them off-centered, kind of like that. Now, I don't know for sure that that's how they're laid out, that they're on opposite sides of that iodine. I won't know that until I look at my chart. So how many electron groups does this have? It has 4 bonds, 1, 2, 3, 4, and 2 lone pairs. So it has 6 electron groups. That tells me, since it has 6, that its electronic shape is octahedral, because it's only based, that's why it's electronic, it's only based on the electron groups. All right, now what's the molecular shape? So to see the molecular shape, I have to do the AB formula. Okay, and if the chart in the book, okay, is the it's like A, B, U, kind of like that. Okay, so if you're looking at that, you know, my chart, my little simple chart's a little bit easier to read on this, but so that is going to be A in the center, B, it has 4 things around it, so AB 4, and then it has 2 lone groups, right? Okay, so I can look over here and find the one with 6 and find the one with 6. 6 groups, it has 4 things bound to it and 2 and so that's telling me that the molecular geometry is square planar. Now, this is where it's important because I can use that information to tell you if those are really on opposite sides of that iodine or not, because if that's square planar, that means it's like this. And the only way it can be like that is if these are even on both sides. If both of those lone pairs were on one side, it would squash that and push it so that it would be in a different shape. So by knowing that it's square planar, which is a nice regular shape, right? Then I know that that is not a polar molecule. Okay, it's not a polar molecule because it is in the shape of a square. All right, and then you've got one I3 minus.